Welcome. I'm not suggesting that you don't know how to count. As I said in previous videos, you probably don't even remember learning. But have you ever stopped to consider the mechanics of how numbers work? Hello, my name is Paul and this is Barebones Tech. The problem with number systems based on tally marks, like the ones used by the Romans, is that they are not particularly practical when it comes to even the most basic of arithmetic, never mind more complex mathematics. We need something better. Let us consider a series of symbols. How many symbols doesn't actually matter. Most of you probably use 10, but I'm going to make up a new system to prove that it's irrelevant. So here are 6 symbols. First, we need to decide on a fixed sequence for these symbols. I'm going with this sequence. Next, we fix one of the issues with the tally system, the fact that there's no symbol representing 0, nothing, the empty set. We will take our first symbol and define it to represent 0, and the remaining symbols will represent the next 5 numbers, like this. We call these symbols digits. So now we can represent values between 0 and 5. Now what? The power of this method comes from its scalability. With a slight tweak, we can represent any number, no matter how large, using just these 6 symbols. To do this, we use something called an algorithm. According to Wikipedia, an algorithm is a finite sequence of well-defined instructions typically used to solve a class of specific problems or to perform a computation. So, we begin by imagining an infinite row of the symbol that represents 0. Of course, if it's infinite, we can't actually write them down, so we only write down the one on the far right of the row. We call this the least significant digit, and it's going to represent our individual values, or units. We'll come back to why it's called the least significant later. The other zeros are there, but not written. Okay, so in order to count, we simply use each of our digits in turn, repeatedly. So when we reach the last one, we simply loop around to 0 again. We refer to this process of moving to the next value incrementing. The opposite, counting backwards or moving to the previous value, is known as decrementing. Here is where the algorithm steps in, as we have one more component to it. To increment a digit, we take the next symbol in sequence. If there are no more symbols available, then we start again at 0 and increment the digit immediately to the left. Notice how this is a recursive process, as we are using our increment algorithm inside itself. In this way, each digit represents how many times the digit to its immediate right has rolled over. Since each time a digit changes, it represents a complete cycle of the symbols in the digit to its immediate right, we consider a change to be more significant the further to the left we go. Thus, the leftmost digit is known as the most significant, which is why the right-hand digit is the least significant. Keep going long enough and we can have numbers with 3, 4, 10, or 1,000 digits. This system is infinitely scalable and requires no more symbols than the 6 we originally defined. Genius. Decrementing is exactly the same, however we simply cycle through the symbols in the opposite direction. Now, there was nothing special about the number 6. I picked it semi-randomly. Most of us are probably familiar with using 10 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. But if you stop to think about it, that works exactly the same way. The number of symbols is referred to as the base. So my system was base 6 and our normal system is base 10. The more common number bases are given names. Base 10 is more commonly known as decimal. It's easy to imagine that decimal became popular because we have 10 digits on our hands. Well, most of us do. But in reality, it's not a very good choice mathematically. The problem is that we can only divide 10 by 2 other numbers, 2 and 5. Other numbers would be a better choice. 12, for example, can be divided by 2, 3, 4 and 6. 16 can be divided by 2, 4 and 8. 20 by 2, 4, 5 and 10. 24 by 2, 3, 4, 6, 8 and 12. and 60 by a whopping 2, 3, 4, 5, 6, 10, 15, 20 and 30. Do these look familiar? Maybe our ancestors weren't as crazy as we thought. There are 12 inches in a foot, 12 pence in an Old English shilling, and 12 months in a year. There are 16 ounces in a pound, and 16 fluid ounces in a US pint. There are 20 fluid ounces in a British pint, and there were 20 shillings in a British pound. There are 24 hours in a day. There are 60 seconds in a minute, and 60 minutes in an hour, and 6 times 60, or 360 degrees, in a circle. Coincidentally, there are also approximately 360 days in a year. We have the ancient Babylonians to thank for this one, as they used a number base of 60. Now, for all of these, we don't use different sets of symbols, but the principle is the same. As always, so what? It might seem like an interesting thought experiment, or something that historians get excited about, but why do we care? Well, the name of this channel is Barebones Tech, and we're interested in technology. In order to understand how computers work, or to build systems that can perform these operations for us, we have to understand exactly how these processes work at the lowest level. For things like computers, which run on electricity, for the most part, it's always easier to consider two states, on or off, voltage or no voltage. If we think of it symbolically, 1 or 0. We have seen that we can create a numbering system based on any quantity of digits, so why not 2? Well, that's exactly what computers do, and base 2 is known as binary. I referred to it in one of my previous videos on computer data types. The word for a single binary digit is a bit. Applying our incrementing algorithm to this number system, we get the following: 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, and so on. Now, computers chew binary up easily, but for humans, we're almost back to the problem we had with tally charts. Even relatively small quantities result in long numbers. To go much beyond 250, for example, will require a whopping 9 bits. As humans, we need to convert this into something more readable. But there's a problem. You see, once we get beyond the number 1, we cannot easily break down the task of converting binary to decimal into subtasks. If we consider 2 bits, we get the equivalent of 0 to 3 in decimal. 3 bits gives us 0 to 7, but 4 gives us 0 to 15. If we consider 2 decimal digits, we get the numbers 0 to 99. That will require 7 bits. 99 is 11000011 in binary. But with 7 bits, we can get up to 127. At no time will we reach a point where a given number of bits will exactly cover the same range as a given number of decimal digits. And that means that when converting, we always need to consider the whole number in one go, which is painful for large numbers. One solution is to ignore the binary values that don't fit neatly into decimal. We can simply use 4-bit binary representation of 0 to 9, which is 0000 to 1001, and simply define as invalid the binary values in the range 1010 to 1111, or 10 to 15 in decimal. We call this binary coded decimal, or BCD. Whilst this makes the conversion to human readable numbers easy, it's not very efficient. For each decimal digit, we're invalidating 6 out of the 16 binary values, or 37.5% of the range. It also makes performing calculations in binary much more complex, since we need to jump directly from 1001 to 100001, which ruins our nice neat algorithm. Okay, so what else could we do? Well, choose another base, of course. We could group our bits into pairs. This will result in 4 combinations, or base 4. Whilst this will halve the length of a number, it's still unmanageable. Grouping our bits into 3s gives us 8 combinations. Base 8 is known as octal and was widely used in the early days of computing, and many computer programming languages still support its use today. The problem with octal is that most modern computers work with binary in multiples of 8 bits. We even give this grouping a special name. We call it a byte. That means that an 8-bit byte becomes 6 2/3 octal digits, and we end up with a similar issue to the one we started with. Moving on, 4 bits gives us 16 combinations to work with, and conveniently splits our 8-bit byte in half. Base 16 is known as hexadecimal, and is the one used by most modern-day programmers and systems. Of course, it doesn't come without issues of its own. We only have 10 symbols to use in our decimal system, so we don't have anything to represent the values 1010 to 1111. We resolve this by using another familiar sequence of symbols with a well-known order, the alphabet, or more specifically the first 6 letters, A to F. So A represents 1010 or decimal 10, B represents 1011 or decimal 11, until we get to F, which represents 1111 or decimal 15. Neat. As an aside, half a byte, 4 bits, is known as a nibble. Yeah, techies have a weird sense of humour. Wow, that was a long one. I hope you found it interesting and that you learned something. I do believe that a thorough understanding of what's actually going on helps to demystify the more advanced topics. So in the next video, I'll be looking at what is probably the most basic of arithmetic operations, addition. If you don't want to miss that, you know what to do. Please subscribe and ring the bell. While you're at it, likes are appreciated and comments welcome. Finally, share this video with other like-minded folks who you think would enjoy it. Once again, my name is Paul, and this has been Barebones Tech. Till next time, thank you for watching.